Hello everyone, this is Dr. Lennon, and today we're going to talk about the average rate of change of a function, which is actually a pretty simple concept. So we'll start with a net change of a function, and from there go to average rate of change. So given a function y equals f of x, we say the net change of f of x from x equals a to x equals b is given by, so the net change is just going to be the difference in the y values over that interval. So the net change will just be f of b minus f of a. So this is the difference in y values over a particular interval. And that's just some terminology. That's something that's natural enough to look at. You might have a population, say in 1990, of 500,000, and then it jumps up to 1.2 million in 2020, and then you would say, okay, I have a net change of 0.7 million. It increased 0.7 million from 500,000 to 1.2 million. But the thing that's more interesting for us is the average rate of change. So the idea for the average rate of change is really the same idea as slope from linear functions, but we're trying to apply it to something that's a little more complicated. So the average rate of change we really can think about as coming from a picture. So we know that functions can have a variety of shapes so long as they pass the vertical line test. And those shapes can be many things, not necessarily lines. So let's think of something that has a little bit of curvature. Maybe we have something like this. This is our f of x. And maybe we have some interval starting at, say, a here and finishing at b. Then it's not a line, but over a small region you might say, well, it kind of behaves like pretty close to a line. A line might approximate it. That's a pretty bad line, but you get the idea. So this dotted line is known as the secant line. And what the average rate of change is the average rate of change is just the slope of that dotted line. So the average rate of change from A to B is the slope of the dotted line connecting them. Sorry, that dotted line is so bad, I really want to fix it. Let me see if I can do better without getting rid of the whole graph. Okay, so let's see. I hate to draw something that terrible. Okay, that's a little bit better. Still not perfect, but... Okay, so you can see how this kind of approximates the idea of slope. We're looking at, we're kind of manufacturing a line from the 2 points that we're looking at, and we want to calculate the slope between them. So in order to calculate the slope, we need 2 points. Well, to get a y value, we can just plug it into the function. So this first point we could say has coordinates a, comma, f of a. And the second coordinate would then have b as the x value and f of b as the y value. So we can write down the formal definition now. how would you compute the slope? You would just plug it into the slope formula. y2 minus y1 over x2 minus x1. Except for instead of using y2 and y1, now we use f of b and f of a. So the average rate of change of a function f of x from x equals a to x equals b is given by so I'll often abbreviate average rate of change just by ARC, and it's going to be f of b minus f of a over b minus a. Okay, so let's go ahead and do an example to figure out some average rates of change. So example, we'll say given f of x equals the quantity x minus 3 squared, find the net change and average rate of change on each interval. So our first interval here, a, will be from x equals 1 to x equals 3. So again, the first task here is to figure out both the y values. So we first want to figure out f of 3. So that's going to be 3 minus 3 squared, which is just 0. And then we also want to figure out f of 1. So that would be 3 minus 1, excuse me, I got that backwards. 1 minus 3 squared, which comes out to 4. So then we can figure, so our net change is just the difference in the y values, right? So the net change is 4 minus, it's going to be 0 minus 4. So you want to keep that order. 0 minus 4, which is negative 4. So we have a net change of negative 4. Our average rate of change is going to be 0 minus 4 divided by 3 minus 1. So that's negative 4 over 2, and we have an average rate of change of negative 2. So those are the two things, the net change and the average rate of change computed on that interval. Let's go ahead and do it on another interval to see if things change at all. B, we have, let's do it for x equals 4 to x equals 7. So again, we want to figure out the two y values. So we start off with, so we're subtracting 3, right? Yeah. So 7 minus 3 quantity squared, which is going to be 16. And f of 4 will be 4 minus 3 quantity squared, which is 1. So for this one, we have our net change, which is going to be 16 minus 1, which is 15. And our average rate of change, which is going to be that 16 minus 1 divided by 7 minus 4. So that comes out to 15 over 3, which equals 5. So we've computed the net change and the average rate of change on both of those intervals. So let's go ahead and make a remark. You may have known this intuitively, or you may have thought about it already, but it's important to point out since we've already studied linear functions. So the average rate of change for a linear function remains the same no matter which interval we choose. Right, the linear function has a graph that's a line, and so if you would draw the line connecting any 2 points, it would be right on top of our line. So that makes sense that our average rate of change would just always be exactly the slope. So we'll point that out. In fact, the average rate of change of a linear function is always the slope. So we'll do two average rate of changes on a linear function on some wildly different intervals. So example, suppose g of x equals minus 4x plus 1. We'll say compute the average rate of change on each interval. So the first interval, maybe we'll do x equals -3 to x equals 2. So I'm not doing net change here, just the average rate of change. So we want to plug in, -2 first. I like to do the bigger one first. So g of 2 is going to be -4 times 2 plus 1. So that comes out to -7. And then g of -3 is -4 times -3 plus 1. So that's 13. So what's our average rate of change? Our average rate of change here is 13 minus -7 divided by 2 minus -3. So that comes out to 20 over sorry, I think I got one of these backwards. Oh, it should be -7 minus 13 on top. So I reversed this. So it's -20 on top. Apologies. -7, the top, minus 13. So we have -20 over +5, which is -4, which is exactly what our slope was. So as anticipated, our average rate of change on this interval was exactly the slope. Let's do another interval that's wildly different. Let's say x equals 10 to x equals 15. The other one was 5 apart. Let's pick a different interval. Let's say 13. I just want to choose a different width. Okay, so we start off with g of 13. So that's -4 times 13 plus 1, which comes out to -51. And then we have g of 10, which is -4 times 10 plus 1, which is -39. So then we have our average rate of change, which is -51 minus -39 divided by 13 minus 10. So we end up with -12 over 3, which comes out to -4. So we get exactly the same answer, even though the interval is different, and both of those answers are exactly the slope of our function. So with these linear functions, that's going to be exactly the case each time. Okay, so let's go ahead and maybe look at a word problem. A lot of times these average rates of change are applied to tables with data. If you don't have a formula, often it's a good way to kind of approximate the rate of change of these things if you don't have any other markers to appeal to. So let's make another remark. in a word problem setting, the units of the average rate of change are the units of output per units of input. So the units of the ARC are a ratio of known units, right? Units of ARC are units of output over the units of input. So that's an important thing to keep in mind when you're trying to interpret such a thing. So let's look at one example where we have a table. So let's say the following table gives the population of a coastal town. Coast, forgot the A. Determine the average rate of change between 1998 and 2001. And then let's say use that to predict the value in 2002. So we have our table here where we have the year and the population. So we have 1997, there were 624 people. 1998, there were 856. 1999, there were 1336. 2000, there were 1578. 2001, there were 1591. And in 2002, there were 1483. So let's go ahead and find the average rate of change. So the average rate of change, the population is the y value, and the year is the input. So we just do the slope formula here. We don't actually have to compute anything. So in 2001, the population was 1591. In 1998, it was 856. And then we subtract the years as well. 2001 minus 1998. So the denominator is 3. What is the numerator? We get 735. So that comes out to 245. And what are the units? That is people per year. Remember, the units of the output are the population, which is people. The units of the input are year. So that's the average rate of change. So to make a prediction, we would take the output from 1591 and expect there would be 245 more people. So in 2002, we predict there are 1591 plus 245, which is equal to 1836 people in the coastal town. So notice that's actually not a great, well, it differs quite a bit from the actual value of 1483. So note that this differs quite a bit from the actual value of 1483. So we have to be very careful when we actually do things like forecasting. We have to be pretty sure that the model is behaving in a way that reflects what we're trying to model it with. In this case, it seems like perhaps the population might be behaving along a linear path for some time, but then it's not doing such a good job later. So sometimes these forecasting intervals are quite limited. But anyway, that's it for average rate of change. And we'll move ahead next time and look at some other concepts with functions. So this is Dr. Lennon signing off.